This is section 4.3, number 5. I've written it out in advance. Here is our problem. Find the general solution of this forced harmonic oscillator. There's no damping involved. First, we go after the homogeneous part. We try, of course, something of the form y is equal to e to the st. Second derivative is an s squared e to the st. We plug that in 9 times e to the st. The e to the st's cancel. We're left with this equation, and s is equal to plus or minus 3i. Using Euler's formula, e to the 3ti is just cosine 3t plus I sine 3t. Each one of these is a solution of the homogeneous problem, and so we have a linear combination of cosine 3t, this real part, and the imaginary part, sine 3t. Together they form the solution of our homogeneous problem. For the particular solution, the strategy is, well, the right-hand side has this cosine 3t here, 2 cosine 3t. If I add an I times 2 sine of 3t, I can rewrite this whole right-hand side as a 2 e to the it, 3it. What's nice about this is it's just an exponential form, and so for our particular solution, we use the method of undetermined coefficients and try something in the form a e to the 3it. Here's the first and second derivative. Plugging in, we realize there's a problem, and the problem is that cosine 3t is one of the solutions of the homogeneous problem, and cosine 3t is the forcing function, and so our particular solution is going to have to include a t in it. So once we realize that we have a problem, the a's all cancel, and we have a function that cannot be expressed, will not allow us to solve for a. Our next attempt is to try something of the form with a t, a times t e to the 3ti. So here's our homogeneous equation. Here's our homogeneous equation. I'm sorry, non-homogeneous equation. Right-hand side, 2 times 3 to the it. We're now trying at 3 to the it. This derivative will require a product rule. Derivative of the first is just this times the second. Now this term has no product rule. When we take the second derivative, we'll just bring down the 3i a e to the 3it. Here, excuse me again, there is a product rule. First we bring down the 3i to make a negative 9. 3i times 3i is a negative 9, a t e to the 3it, and then we differentiate this term. We get a 3i a e to the 3it. We take the second derivative and the function itself, and we plug everything into our equation star, and collecting this 3i and this 3i term, we have a 6ia e to the 3it right here. Here's our minus 9a t e to the 3it, and then here's the 9a t e to the 3it produced by this term in the equation. All of that has to add up to be 2 e to the 3it, and canceling, well, first of all, these terms are identical, so they cancel. And then we realize that we have a e to the 3it on this side, e to the 3it on this side. The only way that we're going to have equality is if 6ia, this coefficient, equals a 2. 6ia has to be a 2. Dividing through by 6i, we're left with 1 over 3i, and an I in the denominator is the same as a negative I in the numerator. This is our value of A. Plugging that back into our particular solution, e to the minus I over 3, t, e to the 3it. Again, applying Euler's formula. E to the 3it is just a t cosine 3t and a t, sine 3t. Taking this imaginary number, multiplying it by this real part gives me the imaginary part. I forgot to write an I. Gives me a t over 3 cosine 3t. But when I take this imaginary term, multiply it by this I get a real part. I times negative I is a positive 1, so I get t over 3 sine 3t. Since our original problem had only a real part to it, in our solution, we only want to take the real part of our solution. And so in this case, the real part of our solution is t over 3 sine 3t. Here is our general solution. It contains the two homogeneous terms in the general solution of the homogeneous problem plus t over 3 sine 3t, the real part of our particular solution. That's it. Thank you.